Hello, my name is Sihui. I'm a student at Colorado School of Mines. Here I will present our paper, Towards General Infeasibility Proofs in Motion Planning. If you have a cluttered cabinet like this, and a home assistant robot of course, grasping something at the back of the shelf would be a very difficult task for the robot. For one thing, the robot doesn't know whether there is a feasible path to reach the back or not, with all the clutter in front. It would try again and again, but if reaching there is just not possible, then it's a total waste of time. In this work, we try to address this important issue of path non-existence. Now let's explain this real-world example more technically. Motion planning for manipulators are usually high-dimensional. To solve these high-dimensional problems, one common approach is to use sampling-based motion planners, like RT or PRM. If a plan exists, they can find high-dimensional motion planning solutions given long enough time. But if no plan exists, as in the cabinet example, they can keep trying forever or until a user-specified timeout. Proving infeasibility in these problems is still unsolved. This work seeks to find infeasibility proofs that can work together with the sampling-based motion planners. An important concept here is completeness versus probabilistic completeness. The main difference is that a complete motion planner can report that there is no solution if a plan does not exist, but a probabilistically complete planner cannot report that, and instead, it would run forever. Most sampling-based motion planners are probabilistically complete. This work focuses on finding a feasibility proof that would make sampling-based motion planners complete instead of probabilistically complete. There are previous works that focus on finding feasibility proof in motion planning. Here we list some of the most related works. The first work relates path non-existence for single rigid objects in 2D or 3D workspace to the problem of caging. The second work proves this connection for a rigid body attempting to pass through narrow gates. These two works focus more on single objects instead of manipulators. The third work proves path non-existence by filling alpha shapes in the configuration space. In this work, scaling to higher dimension depends on high-dimensional alpha shapes, which is still an open research question. The last one uses cell decomposition to achieve resolution completeness, but decomposing the entire configuration space would have a large number of cells in higher dimension. Compared with previous works, our algorithm applies to manipulators and only requires decomposing of a surface in the configuration space. In our work, scalability to higher dimension is still challenging, but is possible because the two key subroutines in our algorithm are a nonlinear optimization problem and a satisfaction problem. Both of them have effective solvers in high dimension. Next, I will talk about the algorithm in detail. The problem is a general motion planning problem setup. The inputs are the robot's configuration space, a start configuration, and a goal configuration. In the middle, our infeasibility proof works together with the sampling-based motion planner. The output is a plan if a plan exists, or infeasibility proof if a plan does not exist. So what is an infeasibility proof? We prove motion planning feasibility by constructing a closed polytope that exists entirely in the obstacle region of the configuration space and separates the start and the goal. As is shown in this figure here, the yellow region is the obstacle region, and the blue lines are the closed polytope. This polytope satisfies the two conditions. First, it exists entirely in the obstacle region, and second, the goal is inside the polytope and the start is outside the polytope. If such a polytope exists, it means the start and the goal exist in disconnected components of the free configuration space, such that no paths connecting them are collision-free. The existence of this polytope is an infeasibility proof. These concepts can be extended to higher dimension. Here is what a 3D robot configuration space infeasibility proof looks like. With this infeasibility proof, here is how it combines with a sampling-based motion planner. When sampling, if a point is sampled in the obstacle region, Then we use this point to grow our infeasibility proof. This is a two-step process. First, we use the point to generate a facet. Then we try to identify the closed polytope from the facets. If there is no polytope found yet, we go back to sampling again. If the polytope is found, then as stated before, an infeasibility proof is constructed. If a point is sampled in the free region, then it goes to build the search tree of any sampling-based motion planner. If the motion planner finds a plan, the process returns a plan. If not, it goes back to sampling again. Here is an animation showing how we generate the polytope in the two steps. First, using points sampled in the obstacle region, we generate a bunch of facets. The facets all exist entirely in the obstacle region. The second step is to identify the closed polytope from those facets. The final polytope is shown in red in the figure. Now we go into details of the two steps. First, let's talk about how a facet is generated. When a point is sampled in collision, we find its closest open edge. An open edge is an edge of a facet that is not shared by other facets. In 2D, an open edge is a point. In 3D, an open edge is an edge of a triangle. At this point, there are two cases. If we can find a hole at the open edge, then we will fill the hole with a new facet. A hole is a small open space among the facets. If a hole does not exist, we need to generate a new collision ball at the open edge. The light blue circle is showing the collision ball in the figures on the right. The new collision ball must contain the open edge, and the radius of the collision ball must be smaller than the penetration depth of its center, so that it exists entirely in the obstacle region. Here, we are talking about the configuration space penetration depth. Besides these constraints, we also want to optimize the ball to be as large as possible and grow onto the direction of the sampled point as much as possible. We set this up as a nonlinear constraint optimization problem. After we generate the ball, there are n-1 points in the ball, that is, the points of the open edge. To form a new facet in the ball, we need one additional point. There are two ways to add the last point. If there are existing points inside the new ball, use the closest one. If there is no other points inside the new ball, then generate a new point in the ball. Together, these n points form the new facet. Because all the collision balls exist in the obstacle region, and all the facets are generated inside the collision balls, the final polytope is guaranteed to be in the obstacle region. Next step is to identify a possible combination of facets to form the closed polytope. We construct a linear constraint satisfaction problem to solve this. There are two constraints. First, we need to ensure the polytope is closed. Second, we need to ensure the polytope separates the start and the goal. We will talk about the two of them one by one. First, to ensure the polytope is closed, each edge of each facet in the polytope must be a common edge with another facet. In other words, there can't be open edges in the polytope. This can be proved by contradiction. The second requirement is that the polytope must have at least n+1 facets. For example, in 2D, we need at least 3 line segments to form a triangle. In 3D, we need at least 4 triangles to form a tetrahedron. We also need to ensure the polytope separates the start and the goal. Here we use the raycasting algorithm. The raycasting algorithm is a simple way to test whether a point is inside or outside a polygon. If a ray starting from a point and going in any fixed direction has odd numbers of intersections with the edges of the polygon, then the point is inside the polygon. Otherwise, it's outside the polygon. We extend the raycasting algorithm in our case by connecting the start and the goal. If there are odd numbers of intersections between the line segments connecting the start and the goal and the facets of the polytope, then one of the start and the goal is inside and one of them is outside. Otherwise, the start and the goal are both inside or both outside the polytope. As shown in the figures here, on the left, the start and the goal are separated by the polytope, and there are odd numbers of intersections. On the right, the start and the goal are not separated by the polytope, and there are even numbers of intersections. For initial demonstration, we applied the algorithm on simple configuration spaces. In this test, the obstacle region is a fixed region between two n-dimensional balls. The goal of this initial test is to show that the algorithm works and can be extended to higher dimension. We did a 2D experiment and a 3D experiment. This is a 2D simple configuration space experiment. The obstacle region is between two circles of radius 0.5 and 2. The faces are growing onto the open edges. In 2D, the faces are line segments and edges are points. It keeps growing until a closed polytope is found, which is shown in red here. This is the 3D simple experiment. The obstacle region is between two balls of radius 0.5 and 2. The faces are triangles. The faces keep growing onto the open edges until a polytope is found. In 3D, an open edge is the edge of a triangle. Next, let's talk about our experiments. We perform experiments on a simulated Jekyll arm. For this manipulator experiment, the goal is to reach the blue object at the back of the shelf. We use Amino for scene setup and robot simulation. We combine our algorithm with RT-Connect in OMPL. Collision checking is completed with FCL, and we use C3 to solve the linear constraint satisfaction problem. We complete 6 scenes that are similar to what is shown in this figure here, and run 12 trials for each scene. In these 6 scenes, 3 have feasible paths and 3 do not have feasible paths. Here are 2 example scenes. They are very similar, however, one has a path and one does not. Could you tell which one is which? Here is the answer. The arm on the left is mounted a bit closer to the shelf, and this small change makes the plan infeasible. Configuration space infeasibilities can be very hard to tell by just looking at it, and our algorithm can construct infeasibility proofs that can tell the user exactly whether a plan exists or not. Here is showing the configuration space infeasibility proof of a Jekyll arm. The faces are growing onto the open edges until we can construct a polytope. The obstacle region is not shown here. This is showing the algorithm profiling results in the 3 scenes when path does not exist. The 3 functions that takes the majority of the runtime are the LCSP solver, the optimization process to find the new balls, and the collision checking. Among these 3, finding new balls takes a large portion. The process to find penetration distance, which is called in each iteration of the optimization process to find new balls, took over 99% of the optimization time. This is definitely something we can improve on for future work. To summarize, in this paper, we proposed a general approach for constructing feasibility proofs in motion planning. This algorithm works with any sampling-based motion planners, and we demonstrated this algorithm in the configuration space of a robot arm. There are still a lot we can do for future work. First, the new ball generation process affects convergence to a closed polytope. We will investigate better heuristics to improve convergence to close the polytope. Second, we need to reduce the computational time. Finding new collision balls is a current bottleneck. We will explore ways to parallelize this process. Also, the LCSP solver can be optimized to reuse previous results when the problem gets larger. All of this would contribute to better scalability in higher dimension. Thanks for your attention.